All right, so any questions? So after my impassioned words yesterday about the SLP and the opportunity it presents, Azad and I decided to postpone the SLP presentations because of current concerns people are having about the health situation. And we're just not sure where the situation is going to go between now and Tuesday, and if by Tuesday things have gotten to a worse point, right? So we'd rather cancel this sooner rather than later because, you know, invitations were sent to the president and such. So, so SLP presentations will not happen Tuesday in the digital lounge, and we'll just do the spring presentations in June. But we will do presentations of your projects in class starting on Tuesday. So I have your posters. If you sent them in on time, they were printed out. I have those in my office. And so Tuesday we'll just come up in class and I'll ask each person to come up front. You can use your poster if you want and just basically talk to the class for a few minutes. Tell us what you're working on, where you are, what roadblocks you run into, any adjustments you made in your project. Basically what you would say to somebody if they came up to you during the presentation and wanted to know about your project. So it'll be just in-class presentations. Tuesday, and depending how many people show up, it may just be on Tuesday or it may be Tuesday, Wednesday. But if everybody who is here Tuesday finishes, then I'm not going to do them on Wednesday and you're going to get a 0. So make sure you come on Tuesday prepared to present, okay? And if we need to go into Wednesday, we'll go into Wednesday, but I don't want this to drag on throughout the whole week with people showing up Friday saying, I didn't show up to present, can I present now? So come to class Tuesday prepared to present, and we'll go on to other days if necessary. All right, everybody clear on that? All right, so questions on Quicksort? So let me run through one more example of Quicksort, and then I'll have you break into groups and work on the board and make sure that you're clear on this, because you'll definitely see one of these on the exam. So let me make a list of numbers. Alright, so list of numbers. We're going to take the rightmost number as the pivot, so I'm going to draw a box around that. And I'm going to move from the left looking for numbers that are smaller than the pivot, and I'm going to move from the right then looking for numbers that are bigger than the pivot. And I'm going to draw my left arrows below and my right ones above. So I start with an 18. 18 is not smaller than 12, so I can't go any further from the left. So now I'm going to switch to the right, and I'm not going to look at the pivot. I'm going to start with the first number to its left. 19 is bigger than 12, so I can keep going. 13 is bigger than 12, so I can keep going. 8 is not bigger than 12, so I stop. And now I take the numbers that I stopped at from the left and the right, and I just swap them. Okay, so my next version of this is going to be the following. And you know, when you're comfortable with this, you can do this by just erasing or crossing out. But I want to do this in a way that shows clearly exactly what's happening. And I strongly recommend, if you're doing this on a test, that you do the same thing so that the person grading it, that's me, knows exactly how you got each of the things that you wrote down. Okay. So I've swapped the 8 and the 18. Here's my arrows where they were, and now I'm going to continue drawing arrows. So I'm going to look at the 10. That's smaller than 12. So I keep going. There's a 6. That's smaller than 12. So I keep going. There's a 14. I stop. Now I come to the right. There's a 2. That's not bigger than 12. It's smaller than 12. So I stop from the right. And now I'm going to swap the 14 and the 2. So that leaves me with 8, 10, 6, 2, 20, 17, 11, 9, 15, 7, 16, 5. The 2 got swapped with a 14, 18, 13, 19, 12. right? Now, if I'm looking at this, if this is what you've turned in, right, I know how you got from here to here. I know you swapped the 14 and the 2 because that's where your arrows were pointing last. If I'm doing this all on one line and I'm just crossing out, it's really hard to know how you got where you're going. And if you make a mistake, right, I can't tell if it's a big mistake or a little mistake. So, so there's my new set of numbers after I swapped 14 and 2, and now I'm going to continue from the left. So I move to the 20, and 20 is bigger than 12, I stop. I move from the right to the 5. 5 is smaller than 12, so I stop. Got to do another swap. All right, so 8, 10, 6, 2, 5, 17, 11, 9, 15, 7, 16. The 5 swaps with a 20, and the rest of this is the same. Redraw your arrows. And now continue. Move to the 17. 17 is bigger than 12. I can't move any further from the left. Start moving from the right. 16 is bigger than 12. That's fine. 7 is not bigger than 12. I have to stop there. Swap those. So 8, 10, 6, 2, 5, 7, 11, 9, 15, 17, 16, 20, 14, 18, 13, 19, and our pivot of 12. For us, we're just always making the pivot the rightmost number. You could do anything else that you wanted, but it's a convenient place to pick. All right, so now I continue from the left again. 11 is smaller than 12, that's good. 9 is smaller than 12. 15 is not smaller than 12, I stop there. Now I move from the right, I come down to the 15, and 15 is bigger than 12, but it doesn't matter because my arrows have met. So I am finished. When your arrows meet, now you only have one thing left to do, which is swap the pivot with the number that your arrows met at. So your final output is going to be 8, 10, 6, 2, 5, 7, 11, 9. The 12 and the 15 will swap. And then I'm going to circle the number that I just replaced with the pivot. And when I circle that 12, what I'm saying is that 12 is where it belongs in the final sorted list. Which means in particular that everything to the left of the 12 must be smaller than 12. Everything to the right must be bigger. So that's one pass of Quicksort. And that's generally what I would ask you to do on a test, is take a starting array, do one pass, and show me what the result is after the pivot is in the right place.
So if you get those, you get basically for each of those numbers. Eventually you get perfectly sorted like from these places.
So what you do from here is you don't repeat that exactly. You basically do a Quicksort on this list, okay, which puts this in sorted order. You do a Quicksort on this list, which puts that in sorted order, and the 12 is already in the right spot, and you're done. So now it's just a pair of recursive calls. Quicksort this, Quicksort that, you're finished. So Quicksort, first you do this process, pick a pivot, move in from the sides, swap when things are out of order. When your arrows meet, swap the pivot with the number that you're pointing to, and then take each list on either side of that new pivot position, Quicksort those. So it's another divide and conquer. And it's not just a matter of taking the 12 and putting it in place with the 15, right? The 14 and the 12 and the 17 and the 18, those had to end up over here on the right. And we moved them on the right by swapping them with things that needed to go on the left. Okay, so it's a minimal amount of data movement, right? We're not shifting things around and moving whole blocks of memory up and down. We're just swapping pairs. Okay, so that keeps it fairly efficient. All right, does this make some sense? All right, so find a spot on the board, find some people to work with. And let's do a passive quick sort in groups.
I thought it was just like, there's more. We don't want
You guys want to keep doing
it?
That's 2 and 4, not 24.
Okay. 24.
It's 2 and 4.
I'll put in commas.
Yeah. 18.
And let's start with 10 as the pivot.
So we start from the left to the
Is it 16 or 1? No, 1 comma 6. 16? Oh, 16.
That's a 2 and a 4 and a 14. There's a comma in there.
Actually, even so, the left has to be left, because it, oh, it swaps. Oh, okay. Oh, yeah, no, so like, we skip the 15, then we stop at the 1, essentially here.
So you want to stop at 15, because 15 is on the wrong side. 15 is too big.
Oh, so,
So you'd have an arrow pointing at 15, but you wouldn't go any further yet.
and the addition flips to the right side.
Mm-hmm.
What?
Do we start on the right or left, or do we start from the
Yeah,
left?
okay.
I probably forgot, I'm sorry.
So start from the left, right? Look at the 15.
I'm trying to
15.
remember that we flagged the need to swap.
Right, so stop there. Now go to the right. Start with the 19. Right. And then swap those two. Perfect.
So then it's
13.
Yeah, it is.
Is that 13? Okay, yeah.
Which also needs to try a lot of processing.
Well, most of the stuff you're writing is the same, so it's already in memory.
Oh, okay, that's true.
That's, so is that fully sorted?
Yeah, it's just being explicit for my
Take,
benefit.
10 right in the middle, and then taking the number on the other side.
I think you flip the 16.
Oh, is that how that?
The
Oh, yeah, I guess because it would be.
the 16 is your next biggest thing.
That's one side.
Alright, I better use this one myself so I know what it should look like. This is a quick sort.
So, and then the two remaining set of numbers on either side of the 10, do you pick the rightmost number and like sort again in that like subset?
I mean, after you're done with this pass.
Yeah, so after you're done.
After you're done with the pass, you take everything to the left of the 10 and everything to the right of the 10, you quick sort each of those.
So you're just taking the rightmost number with those groups, right?
Yeah, yeah.
I think I'm done.
All right, let me do my solution and see if it matches yours.
Oh, I think that's a lot. Mine's on the top. Yeah. Should we keep going after we're done with the first pass?
You can, if you want to practice, you can do the sub lists, but that's as far as I was planning to go. It was just one pass.
So then we're picking what's larger on this side and smaller. Oh, it's. Oh, we're like, so this would be the first one.
All right. How do we do?
Sorry,
Okay, good, good. 10, 15, 12, 14. Cool. That looks perfect.
Oh, yeah. Have fun with it.
I think there are two separate.
There's one side on the side. The 14.
Oh, the last one's on my feet?
Yeah,
Oh,
yeah,
that's
yeah.
on my feet. Yeah, yeah, yeah. You just swap the sides.
Unfortunately, we didn't do that, but I will say that you may not be able to use more stuff, it's typically the stuff.
Anyway, yeah, so make sense? Okay.
Are we doing the next?
No, but, no, I mean, it's for Chris
So-
and keep doing it.
Yeah. Oh, yeah, and then, yeah. It's like, do I have to do this now? Computer
Yeah.
Yes. This is not perfect.
Okay.
The physics is not part of the physics.
It's not.
Right, the dead end square units box of product. The 10 is boxed, it needs to be boxed here, and then turn off the 10 here. That looks a bit square for circle.
Is it?
Okay.
Because I only ran into the greater and less.
So, I was thinking,
No.
Were the ones that were right next to it.
Attached to
Yeah.
it would make sense. That I was
Just off you two in the side.
Okay.
Then yeah, what do I do next one? It's like we've already asked you for all.
So then we swap.
Okay, cool. Okay, so it's whatever the last like greatest one.
Yeah, so.
All right, so any questions on Quicksort? Cool. Go ahead and have a seat.
Oh, okay.
So then we do it again with one spot.
So it has to go in
Like
between.
1, 2, 3, 4, 5, sorry. 5.
All right, so that's a really efficient sort in general, provided that when you're done with each pass, you're roughly cutting your list in half, right? So once you've swapped your pivot with whatever it should be, wherever it should be, right, now you're going to quick sort the left and right halves of the list. If they're not roughly the same size, right, you're losing some efficiency. Ideally, you cut the list in half each time that you make a pass. You end up swapping with a number right in the middle, and now you have to do basically log n passes to get down to a list of length 1, which you don't have to do any work on. But depending on how skewed your list gets split in half or into two pieces, right, you lose some efficiency. So that's n log n average case, but it's n squared worst case. All right, so that's a good sort to know for the exam. So let's talk about heaps. So a heap is a different kind of data structure. It's kind of like, it is a tree, but it's not a binary search tree. Okay, but it is a tree-like structure. Heaps are not a good way to organize information that you want to search. There's not an efficient way to do a search on a heap, but it's a very efficient way to organize information if you want to extract information in a particular sorted order, say increasing or decreasing numbers. Heaps are very efficient. So a heap is a tree. Which has two properties. It has what we call the shape of a heap, which I'll tell you what that is in a second, but it's got to be shaped like a heap. And each node satisfies what we call the heap property. And it almost is like just a pile of numbers thrown in a heap. Okay, it's a very sort of sloppy, quick to put together assembly of data. But it has these two characteristic properties. The first is it satisfies the heap shape. The heap shape is the following. Okay, that's a heap. This is a heap, this is a heap. Everything I'm drawing is a heap. The heap shape means that each level of the tree has to be completely full, except possibly the last level. The deepest level does not have to be full, because if you don't have enough data, you can't fill that up, but it has to be filled in from left to right. So if I were to add a node over here, this would no longer satisfy the heap shape. If I wanted to add another piece of data, I would have to add it right here, the next spot on the lowest level. And the next piece of data would have to go here, and then here, and then here, and then here, and only then, if I added one more piece of data, could I go down to a deeper level. So the heap shape says each level is completely filled in except possibly the deepest level, and the deepest level is filled in from left to right. Okay, that's what we mean by having the shape of a heap. Okay, the heap property, well, there's two kinds of heaps. There's max heaps and min heaps. So in the A section, I talked about max heaps. I'll talk about min heaps here. They're basically the same thing. Replace greater with less than with greater, and top with bottom and bottom with top, and you can turn a max heap into a min heap. So I'll talk about min heaps exclusively for this class, but everything I'm saying also applies to a max heap. It's just a different comparison condition. So a min heap, the heap property is the following. Each node is less than each of its children. So if you look at any node in the heap, its value should be smaller than the values of its children. I'm going to assume that values are unique, so we won't worry about equal then. So each node is smaller than the value of its children. So I can make a heap pretty easily. Here's a 5, 10, there's a 7, there's a 20, there's a 30, here's an 8, and 40, and here's a 33, and here's a 31, and 39. It's a funny 33. All right, that's a perfectly good min heap. Okay, it satisfies the heap shape. Each level is full. 1, 2, 4 things. The last level's not full, but it's filled in from left to right. And each node, if I've done this right, should be smaller than the value of each of its children. Okay, so that's a min heap. All right, what are the operations we can perform on a min heap? One operation is remove or delete the smallest value. So we can't delete an arbitrary value from a heap. We can say, give me the smallest value that's on the heap. Well, where is the smallest value on the heap going to be?
The root?
It's always going to be the root, right? Because of this heap property, which says each node is smaller than its children. Well, if this node was the child of something else, right, that child would have to be smaller than the root. The root's the only node that's not the child of anyone else, so it's the only node that's not smaller than anything else. So this is the smallest. So remove the smallest value. This is the root. So very efficient. Order 1 to find the smallest value in this collection. All right, well, we'll just remove the 5. So that gives us a 5. Well, as soon as we remove the 5 from the heap, it does not satisfy the heap shape anymore. In fact, it's not even a tree. It's 2 trees now. So we've got to do something to turn this back into a heap. And if you and I look at this, we know that the smallest value left over, which looks like a 7, should probably be the root. But if I move the 7 up here, then this thing is 2 nodes that have no parent, right? So the least obtrusive way to replace the root is also the way that preserves the heap shape, which is to take this last node on the tree and move that up to the root. Okay, so replace the root with the last node in the heap. By last node, what do I mean? Lowest level, rightmost. So go all the way down to the deepest level of the tree, take the rightmost node, move that up to the root. So that changes our heap into something that looks like this. Okay, it's a tree, it has the heap shape, but it's not a heap anymore. It's not a min heap because this node up here, the root, does not satisfy the heap property, which says that 31 should be smaller than both of its children. So first we replace the root with the last node in the heap, and then we do what's called down heaping. Okay, so what does down heap mean? Compare a node with its children, and it's supposed to be smaller than its children, okay? If not less than both children, swap it with the largest child. Nope, swap it with the smallest child. Okay, so 31 should be smaller than both children. It's not, so swap it with the smallest child. Let's put a 7 up there, put a 31 there. And then repeat. So now look at the 31. 31 should be smaller than both children. It's not, so swap it with the smallest child. And now look at the 31. Well, it has no children, so it satisfies the heap property. So we've taken our original heap and we've turned it into this thing. Alright, and that's again a heap. It has the heap shape, every node satisfies the heap property. Alright, does that make sense? Alright, so now if we want the next smallest number from the heap, that's going to be the 7. So we'll remove the 7, that's the root. What do we replace the 7 with? 39, because that's the last thing. And then we have to down heap from the 39. So 39 violates the heap property, swap with the smallest child, that'll put an 8 there, and a 39 here. 39 still violates the heap property, swap with the smallest child, puts a 31 there, and a 39, and we're done. So our new heap looks like this. And that's a heap. Do you want a cough drop? Okay. I'm packing like full power. Alright, so that's how we remove things from the heap. You always take the root, that's always going to be the smallest element in the heap, and then to replace the root you use the last thing from the deepest level, the rightmost thing on the deepest level, put it up to the root, and then down heap, which means just move through until you're satisfying the heap property or you have no children, and that gets you back to a heap. Very efficient, okay? It takes one operation to find the root, because presumably you have a pointer to the root of the tree. If you have to navigate through to find the rightmost thing on the bottom layer, that's expensive, but we'll talk about how to fix that in a bit. And then down heaping is just a matter of comparing yourself to both children, possibly doing a swap and repeating. How many times might you have to down heap? It's constrained by the depth of the deepest node, right? The height of the tree. And the heap shape requirement tells us that this tree is as full as possible. So you have n nodes, the height of the tree is roughly log n. Right? We can't have this pathology where we have n nodes and a big long line and our tree has a height of n, in which case we'd have to do n comparisons and swaps to down heap. We've always got each layer full, which means n nodes will fit in a tree of height log n. So at most we're doing log n operations to down heap. So deletion is basically a log n, guaranteed. Right, worst case.
So is the only advantage of this structure is just knowing what the smallest number is?
So this is really well suited when you just want to get the smallest number from the structure, from the collection of data. Which might be the case when, I don't know, you're doing something like, we haven't talked about graph theory yet. I'm hoping to talk about it next week. If not, it'll be in 223. But you know, you have a graph. You have a series of cities. And you have certain roads between certain cities with certain lengths. And you know this from driving around in Portland, right? You might be 1 block away from someplace, but it might be faster to go 3 blocks out of your way to get there because of traffic or construction or one-way streets, right? So, so maybe we want to know for the place that we're at, what's the shortest distance to another place on our graph, right? So if we had all of our distances stored in a min heap, right, we can always find that distance by just pulling off the root of the min heap. Max heaps are used for things like priority queues. If you have a series of queues for managing jobs, but each queue has a different priority, and you want to know what's the highest priority job that's looking for CPU time right now, well, you could store those priorities in a max heap and extract that information very quickly. All right, so deleting is order log n. It's very efficient. Inserting is also very straightforward and log n efficiency. So let's look at the heap we ended up with. So it was 8, 10, 31, 20, 30, 39, 40, 33. So insert 1, add node to last position, which is deepest level, leftmost spot. So in this case, let's add a 7. So I would go down to the deepest level. I would add it to the leftmost open spot, which would be right here. Okay. If my lowest level looked like this, if it was completely full and I wanted to add a new node, I would start a new level and I'd put it in the leftmost spot. Okay. So we're moving across and slowly working our way down. So we could add a 7 right here, and then we upheap. So to upheap, see if this node's parent satisfies the heap property. Is 20 smaller than both of its children? No, it's not. Swap with the smallest child. So put the 7 up there and the 20 down here. And now, looking at the 7, does its parent satisfy the heap property? Is 10 smaller than both children? No, it's not. So swap with the smallest child. And now look at 7's parent, 8. Does 8 satisfy the heap property? Yes, it does. So we're done. And our new heap looks like this. So the 7 went over there, the 30, the 10, the 33, and the 20. And so we've inserted a 7 into our heap. Yeah.
Is the 7 supposed to be below the 8?
Yeah, how did that happen? I stopped too soon. See, I got the 7, so does the parent satisfy the heap property? No, it doesn't. So swap with the smallest child. All right, so there's our heap. This is why we have computers, I guess. All right, there's a heap. And again, there's no rhyme or reason about left or right. Okay, I've got a 33 way over here on the left, and that's bigger than a 31 sitting way over here on the right at a much higher level. That's not a problem, right? The only requirement, each node has to be smaller than its children. All right, making sense? All right, back to the boards. Let's build some heaps. So we will start with an empty heap, and I will give you some numbers, and we'll build them up into a heap, and we'll heapify. We'll down heap and up heap. And once you've done this, it should make good sense. So let's just start off with the number 20. I'm just going to start with an empty heap, and you're going to insert nodes into it.
Okay.
All right, so you got a heap with a 20 in it. Good.
Here's our heap.
Excellent. We got a green heap and a black heap and a blue heap, 2 blue heaps, and a red heap. Okay, so we've got a heap with a 20 in it. Okay, let's go ahead and add a 10. And then you want to go ahead and see if 10's parent satisfies the heap property. And if it doesn't, then you want to swap with the smallest child. So that's up heaping.
Smallest non-null child.
Smallest non-null child.
Because it's about not features.
Perfect.
That's sick.
Yeah, don't compare with nulls. All right, so you've got a heap that looks like a 10 at the root and a 20 off to the left. Now, when you're doing this on a test, it's useful to keep the intermediate stages so that somebody looking at it can tell what went wrong if something went wrong. So let's add a 30. All right, so 30 doesn't take a lot of work to add. You just put it at the bottom of the tree. So let's add a 40. Okay, good. So now do a 15.
That doesn't mean anything. Just somehow else transmitted to me.
Right, so the 15 you have to upheap once,
And then return it.
and then the 10 is smaller than its children, so you can stop upheaping at that point. All right, so go ahead and put in a 5. Good. Good. All right, cool. So try deleting the 5 now.
What was the direction?
The leftmost, I think.
Leftmost on the bottom row goes up in place of the root.
Leftmost or rightmost on the bottom row?
Rightmost. Yeah. Yeah.
Yeah, when you're done.
Bigger than small child. Okay. Yeah, it's fine. Yeah. With all the rules.
Rightmost on the bottom row, yeah. Good. Where are we on the end border? Good.
See if it's still close. Rules. Yeah, I was thinking about.
All right, cool. Everybody's got it. Does that make sense? Right, so you'll probably see a question on the exam with heaps too, with inserting or removing. So that's really all there is to it. To remove, replace the root with the last thing on the bottom row, and then down heap. To insert into the next spot on the bottom row and up heap. And just remember the heap property. If it's a min heap, we want each node to be smaller than its children. And so upheaping is just replacing with the smallest child so that you satisfy the heap property. And keep going till that's satisfied or you're out of nodes. All right, so I want to talk next about heapifying, which is how you take a bunch of data and turn it into a heap. And there's a really clever way to do that efficiently. And then I want to talk about implementing these things without using pointers. So tomorrow's open lab, no lecture. So come in if you want to work on projects or talk about code and so on. Monday we'll finish talking about heaps and some other sorts. And then Tuesday we'll start doing SLP presentations. And then once that's done, we'll probably go on, we'll talk about some graph theory for the end of the course. All right, so I will see you tomorrow if you come in for class or for 2:15.